But light is massless, so I always thought that it shouldn't be affected by gravity. But then I learned that the path of the light can be bent by very massive stars. So what's going on? Why is gravity affecting massless light? Now, for a long time, I thought Newton had no answer for this, but boy, was I wrong. So in this video, we're gonna see first of all how even in Newtonian physics, you can argue that gravity can affect light, but then we will see more importantly how this actually surfaces. A big mystery that was hiding for centuries. And finally, how Einstein comes along, takes it to a whole new level, and he'll help us rediscover. That's right, it's a rediscovery, not just telling you the facts, but how we will rediscover the basic ideas of general relativity. This is the first of a video series on this. So if you're ready to dive deep into this, let's begin. So Newton, help me understand why gravity affects massless light. For that, Newton asks, Mahesh, first of all, what would happen if you were to drop a basketball and a feather in vacuum? Which one would fall first? Well, my answer would be obviously the basketball. The feather would just float over there. But Newton reminds us this is because of all the air particles present in the present over there. What if we got rid of the air and did this in perfect vacuum? Then we'll actually find that the basketball and the feather actually fall together. And we've done these experiments multiple times before, and I've linked below two of my favorite sources. One is in a NASA facility where you actually drop a basketball and a feather in a giant vacuum chamber. And there's another epic video of, well, a hammer and a feather being dropped on the moon. So check them out. The link is in the description below if you haven't seen it already. But this basically means that both the basketball and the feather accelerate down at the same rate, the familiar 9.8 meters per second square. But more importantly, these two have different masses and still they accelerate down at the same rate. This means this acceleration is independent of mass. And now Newton asks, Mahesh, what if we consider even a lighter particle, say a grain of sand? What would it accelerate at? And I'm like, yes, I got it. Even that should accelerate at 9.8 meters per second square near Earth because it's mass independent. And now it asks, Mahesh, what if we consider even lighter particles, say a virus? And I'm like, okay, it's very hard to visualize a virus accelerating down, but it should. It should also accelerate down at 9.8 meters per second square because we've established this, Newton. What's your question? What's your point? Why do you keep asking me this question? And now Newton asks, Mahesh, what if we now consider the lightest particle, light? What happens to it?
Auto insurance all seems the same until it's time to use it. With USAA, it's easy to file claims, schedule repairs, and access roadside assistance right through your app. Or you could take your chances somewhere else. Get a quote today.
Is someone trying to steal your Butterfinger? Call the BFI. Game over. No one lays a finger on your Butterfinger.
No, this cannot apply to light. And Newton says, but why not? We just saw that this acceleration is independent of the mass. Regardless of what mass we're dealing with, it should be true. So shouldn't it also hold for light? So this is how, even in Newtonian physics, we can argue that gravity should affect light, mainly because the acceleration due to gravity is independent of the mass. That means every object should accelerate down at the same rate, and so light should also be accelerated. But I have a problem with this. Okay, here's my counter argument. I'd say, Newton, you remember the force of gravity is given by this expression mg. Well, for light, mass is 0, so the force of gravity is 0. If the force of gravity is 0, then how can there be any acceleration? Acceleration should also be 0, right? And Newton says, Mahesh, be careful, okay? So if you want to calculate acceleration, we have to use Newton's second law, which says this equals ma, and from this, acceleration becomes mg, that is the net force, divided by m. Now, if I substitute mass equal to 0 and say that the net force acting, the force of gravity, should be 0, then even in the denominator, I get a 0. And a 0 by 0, Newton reminds us, is not 0. It's an indeterminate form, which tells us that algebra can't handle it. So that's the important part. 0 by 0 is not 0. So how do you calculate it? Well, you need to find better ways to evaluate, and a better way over here is to just cancel out the masses, and you do indeed find that the acceleration is a constant. It does not depend on the mass, and therefore every object should get the same acceleration. This is why the path of the light can be bent by massive stars, because light is accelerated towards it by gravity. So the summary over here is, because the acceleration due to gravity is independent of mass, light should also be accelerated at the same rate. Now, I don't really find this the most intuitive explanation, mainly because this feels like more of a logical extension and less like an elegant answer to it. But what was intriguing for me is the fact that even if the force of gravity, just because the force of gravity is zero, doesn't mean the acceleration becomes zero, because you end up with